This video accompanies Learning IoT with Python and Raspberry Pi. In this video, you will learn about the Heapsort algorithm.
The Heapsort algorithm is a version of selection sorting that uses a binary heap to hold the elements that remain to be sorted. The advantage of using a binary heap is that it can be implemented using an array or a list, and auxiliary memory is not used when sorting the list. The first phase of the Heapsort algorithm is when the unsorted list is transformed into a max heap, which is a binary heap with the largest value at the root. This task is performed in the build heap function. The max heap is stored in a binary tree. A binary tree is composed of a finite set of nodes. Either the set is empty, or the set is composed of a root, R, and two distinct binary trees, TL and TR, a left subtree and a right subtree. The tree is a union of the root, the left subtree, and the right subtree. The root node of tree T is the parent of the subtrees TR and TL. The subtree TR is a child of the root. The subtree TL is also a child of the root. Each subtree is also a binary tree. A binary tree of height h has at most 2 raised to the power of h plus 1, minus 1 internal nodes, and at most 2 raised to the power of h leaves. The height h is the length of the longest path from the root to a leaf. The binary tree on the left has a left subtree. The binary tree on the right has a right subtree. Both of these trees have 3 leaves. Initially, the data to be sorted is stored in a complete binary tree, but the data is not heap ordered. The complete binary tree is a binary tree of height h with the following properties. If h is equal to 0, the left subtree is an empty set and the right subtree is an empty set. If h is greater than 0, either the left subtree, TL, is a perfect binary tree of height h minus 1, and the right subtree, TR, is a complete binary tree of height h minus 1, or the left subtree, TL, is a complete binary tree of height h minus 1, and the right subtree, TR, is a perfect binary tree of height h minus 1. A perfect binary tree is one where all the internal nodes have 2 children and all of the leaves are at the same level. Here's an example of a complete binary tree. Here's another example of a complete binary tree. A complete binary tree is a tree in which all the levels are full except for the bottom level, and the bottom level is filled left to right. Each subtree also has a parent node with 1 or 2 child nodes. Next, let's examine how a complete binary tree is stored in a list. The root is at position 0. The 2 children of the root are at positions 1 and 2. For each node I, the left child is at position 2 times I plus 1, and the right child is at position 2 times I plus 2. Let's examine the complete binary tree with the indices. Heapifying the list is done by the build heap function. This will create a max heap from the unsorted list, since the complete binary tree is not initially heap ordered. The build heap function heapifies each subtree from the bottom up. The build heap function starts calling the pushdown function with size divided by 2 minus 1. The reason we start at position size divided by 2 minus 1 in the list is that that is the last node in the complete binary tree which has a child. The data in the max heap must satisfy the condition that every node in the heap has a parent node which contains an item with a value greater than or equal to the value of each of the child nodes. The pushdown function sets the child to position 2 times I plus 1, which is the left child of the current node. If there is a right child, then the position of the right child of the current node is at position child plus 1. If the right child's value stored in my list at position child plus 1 has a value greater than the value of the left child at my list at position child, then the value of the child will be set to child plus 1. This value, stored in the child variable, is the position in the list which will have its value compared to the value in the parent node's value. which is in my list at position I. Recall that the value of my list child has the larger of the two values in the child nodes. If the parent node has a value greater than both of the child nodes, break, since the condition is met that the parent node contains a value greater than or equal to each of the child nodes. The while loop continues to move the value at node I down the tree by swapping elements until a leaf node is reached, or both of the children of node I have values which are smaller than the value in node I. If both of the child nodes are less than the parent node, there's no swap. If the right child has a value that's greater than the left child, then we'll swap that value with the value of the parent node. If the left child has a value greater than the right child, we'll swap that value with the parent node. If both of the child nodes have the same value, which are greater than the parent node, then the value that's in the left node is swapped with the value in the parent node. So let's look at building a heap. The child node, or nodes, which are furthest down in the tree, are compared to the parent. This is at depth 3. If the child node is greater, then swap the values. There is no swap in this case since 6 is greater than 5. We'll go to the next node to the left in the tree and swap the value of the child node with the root node since 7 is greater than 2. Go up to depth 2 and swap 8 with 5, since the child node has a value of 8, which is greater than the parent node, which has a value of 5. And this continues until the list is a heap. Swapping the value in the child node with the value in the parent node is done by calling the MySwap function. The MySwap function swaps the values in the two nodes. A temp variable holds the value at position I, since this item in the list will be overwritten with the value at position J. The value at position J in the list will be then assigned the value stored in temp. The second phase of the heap sort algorithm is the sorting phase, and a selection sort is used. A straight selection sort performs a linear search of the unsorted items in order to find the position of the largest item. The largest item is swapped with the last item in the list. The last item in the list is now in a sorted sequence. A linear search of the unsorted items is done in order to find the position of the largest item. This does not include the values in the sorted sequence. The largest item is swapped with the last item in the unsorted list. The next to the last item in the list is the second largest item in the list. The last two items in the list are now part of the sorted sequence. This continues until all of the items are in the sorted sequence. This algorithm is not efficient, with the best case, average case, and worst case running times on the order of n squared, where n is the number of items in the list. The sorting is done in the Heapsort function once the list is heap ordered. The binary heap stores the elements in the list that remain to be sorted. The sorted sequence is obtained by repeatedly withdrawing the largest item from the max heap. The largest item is at the root, which is stored at position 0. The item stored at position 0 is swapped with the last element in the max heap. This corresponds to the node which can be removed and still leave a complete tree for the heap. This last element is withdrawn from the heap, and the last element now has the largest value in the list. This last element is part of the sorted sequence and is thus no longer considered to be part of the heap. The heap size is now decreased by 1, but the complete binary tree is no longer a heap. Thus, the pushdown function must be called to heapify the elements which remain in the complete binary tree. This process continues until all of the elements are withdrawn from the heap and are a part of the sorted sequence. This algorithm provides a significant improvement in efficiency over the straight selection sort, since each element in the heap does not need to be searched in order to find the largest element, since the largest element is always at index 0, which is the root of the max heap. So we'll start with an array containing the max heap. The value of the element at position 0 is swapped with the last element in the list. 8 is swapped with 5. The sorted sequence now contains 8. The remaining elements are no longer heap ordered, so the pushdown function is called to heapify them. Now that the elements are again heap ordered, the element at index 0 is swapped with the next to the last element in the list. The last 2 elements in the list are now part of the sorted sequence. The remaining elements are once again heapified and sorted into a max heap. Let's create the Heapsort program. We'll first define a function that's called printList. This function takes 2 parameters, myList and size. The function will use a for loop to print out each one of the items in myList. We'll format the output with :2D to give 2 spaces for each one of the items. We'll use a keyword argument for end to say that we don't want to go to the new line when printing out each element. Outside of the loop, we'll just print a new line by calling the print function. Let's save this program as heapsort.py. We'll run the code just to ensure that we have not made any syntax errors. We'll create a mySwap function which will swap the values of the elements in the list. We'll pass in myList, I and j. We'll store the value of myList at index I and temp, since we'll overwrite myList I with the value in myList j. We'll set the value of myList j equal to temp. The pushdown function takes in 3 parameters, myList, size, and I. The purpose of the pushdown function is to ensure that each parent node has a value that's greater than the value stored in the 2 child nodes. This is going to perform the steps which will heapify the list. We'll put in some print function calls to see the intermediate steps of heapification. We'll set the child value to be 2 times I plus 1. Recall from how the values were stored in the list that the child node is at position 2 times I plus 1, and that's the left child of the current node. And the right child is going to be at 2 times I plus 2. We're going to determine if there is a right child node at child plus 1 position. If there is, we're going to see is that value that's stored in myList, child plus 1, greater than myList child. If it is, we'll set child equal to child plus 1. Since this means that the value of the item in the right node is greater than the value of the item in the left node, child will then be equal to 2 times I plus 2, which is the index of the right node. We'll then determine if the value of the current node is greater than or equal to the larger of the 2 child values. If it is, we're going to break because there's no need to swap the values since we've already met the condition that the parent node has a value that's greater than or equal to both of the child nodes. If one of the child nodes is greater than the parent node, we're going to swap those two values by calling the mySwap function and passing in the position I of the current node and child, which is the position of the node with the greater value. We'll again print out the list to see the intermediate steps of heapification. Let's next create the build heap function. This function just takes one parameter, myList. We'll determine the size of myList by calling the len function and passing in myList as an argument. The build heap function starts calling the pushdown function with size divided by 2 minus 1. The reason we start at position size divided by 2 minus 1 in the list is that it is the last node in the complete binary tree, which has a child node. Now notice the size //2, that allows us to perform integer division. We'll go all the way down to index 0, which is the root of the complete binary tree and the first element in the list. We'll call the pushdown function by passing in myList, size, and I. We'll again run the code to ensure that we haven't made any syntax errors. We'll define the Heapsort function, which takes myList as a parameter. We'll determine the size by calling the len function and passing in myList as the argument. We'll call the build heap function and pass in myList as the argument. We will display the intermediate values inside of myList to see how the list is being sorted into a sorted sequence. Next, we'll go through each one of the elements in myList and we'll swap the element that's at index 0 with the last element in the list. The last element in the list is a node which can be removed from the binary tree and still leave a complete binary tree. Remember that because this list is heap sorted, the element that's at index 0 is the maximum element in the list. By putting this largest value at the end of the list, this will now be part of the sorted sequence and no longer will be part of the unsorted heap. Since the elements that are in the heap are no longer sorted, we'll need to call the pushdown function in order to create a list, which is once again heap ordered. Notice when the pushdown function is called, with myList, I, and 0 as the arguments, we're not passing in size for the number of items in the heap. We're passing in I. That's because we have actually removed some of the items from the heap and moved them into the sorted sequence. We'll once again print out the elements in myList. In the main function, we'll define a list called HList with the same items as we saw in the PowerPoint presentation. We'll print the items in HList, and then we'll call the Heapsort function and pass in HList. After we call the Heapsort function, we'll print the HList in order to see that the items have in fact been sorted into ascending order. And then we'll call the main function. Let's run the code. The Heapsort function calls the build heap function, which will heapify the list. And you'll notice during this process of heapification that the parent node has a value which is greater than or equal to each one of the child nodes. The list is now a max heap. Next, we'll use a selection sort to remove the largest item and move it to the end of the list. Notice that each time the maximum value is removed from the heap and put at the end of the list as part of the sorted sequence, the size of the heap is decreased by 1. Therefore, only those unsorted items remain in the heap, which again is heapified. This continues until all items are in the sorted sequence. This completes the lecture on sorting a heap.
Go to www.learningiot.net for information on where you can buy Learning IoT with Python and Raspberry Pi.